Welcome back to my Billet intake manifold build series. I'm teaching you how to build an intake manifold like this from start to finish, from design all the way to machining. If you're new here, go back to the beginning of the series and start there. I don't want you to miss any of the information I'm sharing there. If you're not new here and you've been following along, let's get back into Fusion and get going. I have an absolute buttload of time into this project, so please support the channel, hit that subscribe button. Welcome back to the channel, guys. Let's get right into the questions from the last video. Some of you really want to see clips of the actual machining process of some of these toolpaths and stuff that we're talking about. And to be honest, I just didn't have a good way to film those when I made these parts, but I'm going to try to solve that in the future and figure out a way to get some more footage for you guys. Somebody asked why I didn't just use the countersink hole function in the hole creation tool when I was making the countersunk bolt holes in the fuel rails. Yes, I know that's a function of the hole making tool, but sometimes I just find it easier to sketch the circles and just extrude it. But it is there in the hole making tool. You can designate your hole size, your countersink size, and the depths of both of them. But for me, sometimes that just takes a little bit more time. If I was doing more than just the 2 holes I did on that fuel rail, I might think about using that function. But in that particular instance, it was easy just to draw the circles and extrude them. Sometimes I do use it, sometimes I don't. Somebody commented on how I was doing these injector surfaces, telling me that if I had the sketch that was inside the body, it wouldn't allow me to extrude to the body, but if I offset that sketch plane up to where the sketch wasn't inside the body, I could actually start that extrude offset from that surface or plane and still be able to extrude to the body. I'm not sure if that works, but I'm going to try it in the future. So thanks for that suggestion. A couple of people asked about the cutting time or machining time of that first operation on the lower runners. Parts like this take a long time. There's a ton of roughing and a ton of surfacing. I don't remember exactly, but I want to say that first operation took 5 or 6 hours to machine. Some of that is due to the speed of my 4th axis because it's kind of slow, so I actually have to limit the feed rate so that the 4th axis can keep up. I do think a newer, faster machine would do it quicker, but in general, parts like this take a long time to machine. Somebody asked about why I chose the order of operations in the toolpaths that I chose, and they'd like me to elaborate on that further. I think that most of that just comes down to experience. There's obviously a certain order that you have to do things in. You need to rough out the part before you finish it, but the rest of that finishing probably comes down to mainly limiting tool changes so that you're not pulling up a different tool before you go back to the previous tool. So trying to keep all the operations of that tool in a row before you change tools, just in order to save time. So I'd say that's the main reasons, just the necessity of roughing before finishing and then limiting your tool changes. And then lastly, somebody asked about how I designate where to draw my sketch curves to guide my tools on the 4-axis toolpaths. And I think that's going to be easier to explain if we're looking at the software. So let's get into Fusion. Okay guys, so getting into Fusion here, I've went through and pulled up all of the sketches that I've used in these lower runners to guide the geodesic toolpaths that I used. And the question was basically, how do I figure out where to put these? So I think that probably these outer ones are the easiest to explain because we can see the center line and the entire toolpath. The reason that I had to use a geodesic on this is because it had to get down along this flange and it had to get underneath the lip of this flange. So it had to change angle as it machined this surface in order to complete this toolpath. And my guide curve is this line here. So if we look at that from kind of the side, you can see that the center line of the tool is here. So it's able to get kind of up under this lip as much as it needed, and it's able to get along this face here. So the guide curve point is just inside those faces so that the tool having to go through that center line can machine that whole surface. So as far as where to put this, I just typically sketch something that looks close, and then I'll go through and create the toolpath, and then maybe I'll move this sketch around a little bit to see if the toolpath comes out better or worse. I'm sure there would be a good way to like draw a sketch more technically with more data, but in my opinion, it's not as important as you might think. So as long as you're getting a full toolpath and getting as much of the part as you can reach, that's the whole goal really. So for instance, on these lower ones here, so these are the guide curves that I used for my geodesic toolpath coming from the bottom side here. That's not the right one. There we go. So the placement of this is really just in order to reach as much of that surface as you can while the tool is going through this center line. And the other side of that is trying to get the tool to not tilt more than it has to reach this surface. So I actually get a lot more tilt here at the start of the toolpath. At the start of the toolpath, this line could be way out here in space because it wouldn't matter as much. But as it gets deeper into this part, this center line needs to be closer to the part so that the tilt angle is centered on that sketch curve. So I don't know if that's easy to understand or not. Hopefully it is. But basically I'll just draw this curve, generate the toolpath, and then move this curve around a little bit in the design side and see if I'm getting a better or worse toolpath, and that kind of helps you figure out which way you need to go with it. So hopefully that makes sense to you guys. It's kind of a trial and error thing for me. If this was a 5-axis toolpath, you could set the tilt angle and the lean angle for the tool to avoid the wall, and it would probably finish this toolpath even nicer still. But that's how I'm having to achieve it with only 4 axes. So hopefully that makes sense to you guys. So let's get into lower runners op 2. So first let's talk about the trunnion table. So first I needed to design the trunnion table to interface with this finished side of the part. So I basically used the same trunnion table, it's just on a different plane. If we turn on the multiple trunnion tables I had for this part, here's my op 1 trunnion table, and this one's op 2 trunnion table. And this one, the bolts interface with the threaded bolt holes that are in the part. So I just used like a tight hole here that would interface the bolt really tightly, and then that just threads into the threaded holes that are in the part. And that's what locates the part for the second operation. I also again created the sketch to give me my XYZ0. And I didn't really touch on this in the first cam video, but this sketch is a known distance off of my trunnion table. So my trunnion setup that I built makes this surface here exactly 3 inches from center line. But what I did was I made this sketch 3 inches and 10 thou from center line. So that way when I put a new trunnion table on here, I can actually machine this surface flat with it bolted in the machine on the trunnion. So that way I know it's a dead 0 point for the part. So this sketch is 3 inches 10 thou from this surface. And my trunnion rotation point is actually 3 inches. So I'll take 10 thou off of this part to clean up that surface and make it dead flat to my A0. So that's basically my setup for this second operation on this part. Okay, so let's look at lower runners op 2. So in this setup, I'm using, as the stock, I'm using from preceding setup, and I've got continue rest machining clicked. So that's why it's showing the stock that I have left, and we can do toolpaths using rest machining based on the remaining stock instead of the entire block. So beyond that, my initial setup's the same. I'm using the same sketch as my center line for my work coordinate 0. The part's bolted to the new trunnion that I just showed you. I did have to pay attention to how I bolted this thing on because the flange is symmetric and you could bolt it on either way, but this part is actually not symmetric due to this EGR flange over here. It's not on the other side. So I had to make sure I put it on there right, but beyond that, pretty simple setup. So let's look at the first adaptive toolpath here. So you can see that using that rest machining and adaptive 3D roughing, I'm able to basically clear out almost all that's left of the material on this part. And then in the adaptive toolpaths after that, I just had a little bit of material left that I had to get under these flanges that I had to get at an angle. So that's what those two toolpaths are. So pretty much just 3 small roughing toolpaths left on this part, and I have pretty much a complete part that just needs finishing. So from there I did a contour around the bottom side of this head flange here to finish that flange surface. Again, using shortening of the chain to get the lead in point where I wanted so that we're not cutting that whole flange again. And the blend point would be kind of at this outside edge of this arc here, so it'd be barely visible. And then I just did that again on the other side. So now we have basically those whole head flanges finished and the entire rest of the part roughed out. So from there I did a steep and shallow toolpath. Steep and shallow is again a toolpath that you will need the manufacturing seat for. You could also do this with like a parallel toolpath or something like that, but the steep and shallow seems like it does a really good job here, so I used it. And since I have the manufacturing seat, I can use it. So I use steep and shallow there. What that does is basically does a kind of a scallop toolpath, and then it turns into a contour toolpath as it gets to a steeper portion of the part. Again, did that on both sides to finish out underneath those flanges. Here's where I start finishing the runners. So I did use a geodesic toolpath in full 4th axis simultaneous. That's why the linking lines look a little bit funny, but that's what I used to finish out the bottom side of these runners. If we look at that toolpath, you can see that I had a guide curve right up the center of the part here that I could use for the center line of that tool. So that's this sketch curve here. So again, using that full 4th axis simultaneous, geodesic toolpath and using the guide curves, so using the same side of the surface that I used in the first operation outside of the runners. So I'm using those same guide curves to guide this geodesic toolpath. Those are selected here, open chain 1 and 2, and selecting the fixture as avoidance, the whole model as avoidance, and only having my drive surface, that surface that I want to machine. So that's it for finishing that top of that runner, and then I just did that to each one. So pretty simple there. And then I just did a couple little toolpaths here. This is a geodesic to finish out just a little portion that I couldn't reach from the top side. Same on the other side. And then a couple contour toolpaths to deburr this part. So pretty simple on the second operation. The bulk of the work was done on the first operation. That's it, that part is finished. Now, if you want to see how these toolpaths function here, we can go into simulate. I can wait for that to process, and then I can show you how this toolpath functions here. So you can see that some of these are already finished. We're probably doing this one here. So I'll slow this down, and you can see how the part comes in at that funky angle. It's due to the start point of the toolpath being on that end of the flange, so it needs to start at that angle. And then as it machines the part, we have tilt built into the tool using the 4th axis. You can see how the toolpath functions by centering itself around that sketch curve that we used as the center line of the tool. You can speed that up a little. So that's what it's doing, machining the toolpath. So you can see how powerful those simultaneous 4-axis and 5-axis toolpaths are, because we can machine that whole surface without risking colliding the tool with the part or the holder with the part, and finish these surfaces that have angles that you can't get to in a single operation with just positional. Pretty cool. So that's that center runner there finished. So this is going to be a bit shorter video because that second operation is so much more simple than the first. But hopefully you guys are starting to get your head wrapped around the order of operations on how I did this and how to use these 4-axis toolpaths, especially the simultaneous toolpaths. And if you are doing complex parts like this, I do recommend getting that manufacturing extension, because it's definitely worth it if you have the capability of doing these simultaneous toolpaths in your machine. I really appreciate all the views and all the comments you guys are leaving. Please continue to do that. These are not low effort videos and they do take quite a bit of time. So again, like, share, subscribe, leave your questions down below, and we'll see you in the next video.